Hi everybody, I hope this video finds you well. In today's video, we're going to be working through practice number 8, which focuses on concepts from the sampling distribution as well as one sample mean procedures. As always, I would recommend that if you haven't already completed these videos, I would make sure to go ahead and pause this one and finish up watching the videos related to the sampling distribution as well as one sample mean procedures. And I would also recommend making sure that you've tried the 2 questions on this practice before watching the solutions video. If you've already done that, if you've already watched those content videos and tried this practice on your own, well, then we can go ahead and get started. So let's take a look at question 1 here. So question 1 says we're going to suppose that an airline is studying the number of passengers on each of its commercial flights. So we know that their planes have a maximum capacity of 180 passengers, and they find that after studying their flights that the average number of passengers is 168. Notice that that should make sense. The average is a little less than the maximum because obviously it couldn't be over the maximum, with a standard deviation of 24 passengers. So this is telling us stuff about the average of the population and the standard deviation of the population. We're going to do several things with this. The first part, in part A, is we're going to try to describe the most likely shape of the distribution. So that, remember, our choices for shape in this class are between normal, left skewed, right skewed, and uniform. And then in B, C, and D, we're going to calculate some probabilities. So let's go ahead and get started on this. We'll give ourselves a fresh sort of page to work on, and we'll start with part A here. So to quickly summarize the information that we have, so for question 1, we know that they have this max capacity is 180, and we know the average, if we go back, was 168, and standard deviation was 24. So the first thing we'd like to do is we'd like to talk about the shape. So again, for possible shapes, it could be left skewed, right skewed, normal, or uniform. Now, a couple things we should mention here. First, from sort of a problem-solving perspective, we've done a lot of examples and problems where we are assuming, or we're told in the problem, that the distribution is normal. In this case, it wasn't mentioned that it was normal. So most likely the shape is not normal, because if it was normal, that would probably be stated in the problem. So we can sort of rule out that this guy has that normal distribution. So instead, we're probably thinking that the shape is perhaps left skewed, right skewed, or uniform. How do we make the decision, since we don't have the raw data in front of us? Remember, if we had the raw data in front of us, we could put it into something like a histogram or a stem and leaf plot and actually look directly at the shape. But how can we do it just using these summary statistics of the average and standard deviation? Well, the idea here is that we can sort of compare this average against some of the restrictions on the amount of passengers. The amount of passengers, if we think about it, has a minimum value. The lowest number you could ever have is 0. And the highest, well, we know is 180 because that's the maximum capacity for these planes. This average, 168, is pretty close to that maximum. And we can probably reasonably assume that a lot of the flights are near the average. Now, it's not a hard and fast rule in statistics that there needs to be lots of individuals near the average, but generally you should have a good amount of your population near the average value. I mean, that's what makes it the average. So if we think about that, if we're sort of drawing out what a histogram would look like, we're sort of saying that 0 is the lowest possible value and 180 is the highest possible value. And of course, 168 is somewhere pretty close to 180, somewhere like that. So if we think about that, we're saying that there should be sort of tall bars over here. Maybe something that looks like that. There should be lots of individuals clustered near that average. Again, that's not guaranteed, but it's most likely the case. Okay, so now where is there room for a tail? Well, there's no room over here. Maybe it is true that they don't have a lot of flights that have, 180 people, but overall, there's just no room for a long tail. However, there is plenty of room for a long tail over here. Maybe they have very few, very infrequent flights that only have like 100 passengers or something. In other words, where the plane is half empty or something like that. What this is telling us is that the most likely shape, just by the restriction of this maximum capacity, must be most likely left skewed. So this shape is most likely left skewed. And again, the real logic behind this is that there's just no room to the right for a long tail. So the shape of the population is most likely left skewed. So in other words, this population has an average of 168, a standard deviation of 24, and a shape that is most likely left skewed. Now, that means that working with the population is very difficult for us because, as we've seen in this class, we mostly like to work with normally distributed populations. So the fact that the shape is mostly left skewed really limits the amount of analysis that we can do. It turns out to not be as big of an issue, though, because if we look at the follow-up questions that we're going to do in B, C, and D, we're not going to talk about individual flights from this population. We're going to talk about groups of flights from this population. And that we do know how to analyze using the sampling distribution. So let's go ahead and take a look at the next part here, part B. We want to find the probability that on 35 randomly selected flights, the average number of passengers is less than 175. So let's go ahead and just write out what we're going to be doing here. We want to take the probability that 35 flights have an average less than 175. I believe that's what we said there. Yep, there we go. Okay, first thing, as we talked a lot about this, if you see that mention of the average of a group, that immediately tells you that we want to make use of the sampling distribution. Because what fundamentally is the sampling distribution? It's the distribution of the averages of groups of a particular size. And keep also in mind that the sampling distribution depends on the size of the sample. So how large are the samples or groups in this case? Well, we know that we're talking about groups of 35 flights. So this will be the sampling distribution with n equals 35. Now, we discussed the central limit theorem, which tells us how the sampling distribution is related to the population, but it is not the same. So we need to go ahead and actually make sure that we understand what's the mean of the sampling distribution and what's its standard deviation and what's its shape. We can get all those because we know the average and standard deviation and shape of the population, but we do need to perhaps change some of them since this is the sampling distribution now. All right, so we need to know the mean of the sampling distribution. Keep in mind the mean of the sampling distribution is denoted with the mean, our standard mu, but with that subscript of x bar indicating it's the average of the averages, right? Because that's what the sampling distribution is doing. First part of the central limit theorem tells us that the average of the sampling distribution is the same as the average of the population. So the average for our population was 168, so it'll be the same for the sampling distribution. The next component is that we need the standard deviation of the sampling distribution. This one, right, we talked about the second part of the central limit theorem, since it's the population standard deviation divided by the square root of n. So in this case, it would be the original population standard deviation, 24, divided by the square root of n, which in this case is 35. So it'd be 24 divided by square root of 35. If we go ahead and do that calculation, we should say that we get approximately 4.06. So, as we discussed when we first introduced the central limit theorem in the sampling distribution, groups always show less variation than individuals. So notice that the standard deviation for individual flights is pretty large, 24 passengers as the standard deviation, whereas the standard deviation for groups of 35 flights only has a standard deviation of 4.06. So this sampling distribution standard deviation will always be smaller. All right, let's go ahead and talk about the shape as well. Well, we know that the population is most likely left skewed. So what happens when we take groups of 35? Well, the central limit theorem assures us that the sampling distribution will always be more normal than the population. In fact, we sort of gave a cutoff and we said that as long as the sample is size 30 or more, it doesn't matter the shape of the population, the sampling distribution will be approximately normal. So in this case, we can say the shape is going to be approximately normal since n greater than or equal to 30, right? And of course, 35 is greater than or equal to 30. So now, not only have we figured out this average, the standard deviation in this shape for the sampling distribution of groups of size 35, we also have all the information that we need to actually solve the problem. Because we have the mean, we have the standard deviation, and it's approximately normal, so we can use our standard z-score table A approach. So let's go ahead and do that. We'll draw ourselves a bell-shaped curve. Let's go ahead and label our middle at 168. We're looking for the probability that 35 flights have an average less than 175. So 175 would be somewhere over here because it's bigger than the average. And of course, we want to shade into the left because we want the average less than that. So we're trying to determine this shaded area. Immediately, we should have a sense that our answer is probably going to be something over 50% because we've shaded in at least half of the graph plus some more. All right, let's go ahead and find that z-score. So z is going to be our point of interest, 175, minus our mean, which is 168, divided by the standard deviation. And of course, we want to use the standard deviation that applies to averages of groups of this size, which is at 4.06. So we put that in there. We go ahead and we get the numerator first. So 175 minus 168 is going to give us 7 divided by 4.06. And then if we go ahead and do that, we should get a z that is approximately 1.72. So we'll go ahead and, just so that we can keep track of that, we'll go ahead and do that on table A now. So we're looking for 1.72. So let's go find table A. We have it at the end of this document, 1.72. So there's the 1.7, there's the 0.02. Intersecting those together gives us 0.9573. So we want 0.9573. So this gives us 0.9573. We can draw that onto our diagram. Remember, table A always tells us what's to the left. So this tells us that this stuff this way is 0.9573. Does that match up with the shaded area? Yep, it does, right? We wanted the stuff to the left. Table A tells us the stuff to the left, so that is our probability. So we just figured out that the probability that that group of 35 have an average less than 175 is 0.9573. Now, this does not mean that every one of the 35 flights will have less than 175 passengers. This is saying that once we take those 35 flights, average their number of passengers together, the chance that that average will be less than 175 is 0.9573. So that means that some of them could be at like 178 or 180 passengers, but there's enough below 175 that the overall average, once we look at all 35 flights, is going to be less than 175. Okay, so main ideas here is that we saw that we had a group and we were talking about the average of a group. Average of a group is always analyzed using the sampling distribution. When we talk about the sampling distribution, we have to know the size of the sample. That size of the sample is going to impact what the standard deviation is, since it's the original standard deviation divided by the square root of n. And it also told us that the shape was normal since we had a group of size 30 or more. All right, let's go ahead and try something similar to this with part C. So let's give ourselves a blank page again. For part C, we want the probability that on 40 randomly selected flights, the average number of passengers is more than 170. So let's go ahead and do this. So for part C, we want the probability that group of 40 has an average above 170. So once again, notice that we have this group of 40 with an average being greater than 170. So this tells us that we want to use the sampling distribution. Now you might say, can we just reuse everything that we had from the previous part? Well, unfortunately not, because now the group is a different size. The group is size 40, so we are working with a different sampling distribution. This is the sampling distribution with n equals 40. All right, so let's go ahead then and analyze this. So what is the mean going to be? Well, the mean of the sampling distribution is always the same as the population, doesn't matter what the sample size is. So this will still be 168. The standard deviation does change. It'll be the original standard deviation, 24, divided by the square root of 40. We're dividing by square root of 40 because now the group size is size 40. So 24 divided by square root of 40, that should give us approximately 3.79. So notice the standard deviation is even smaller than the one we had in B because the group is larger. So the larger the group, the less variation the average of that group is going to display. All right, and what about the shape? Well, again, the population was probably or most likely less skewed, but once again, we're talking about a group that is size 30 or more. So the shape is going to be approximately normal since n is greater than or equal to 30. And that's a great news for us because that means we can use our table A z-score method to analyze this. So let's go ahead and do that. We can draw our bell-shaped curve. The middle is still going to be at 168. Our point of interest is 170, which is a little bit above 168. And this time we're interested in the average being above 170, so we will be shading in this stuff to the right, all the values that are above 170. All right, let's go ahead and calculate our z-score. So z is going to be our point of interest, 170, minus our mean, 168, divided by our standard deviation that applies to this sampling distribution, which is at 3.79. So let's put that down there. Of course, we do our numerator first, which is 2 over 3.79. And then once we do that division, it looks like our z here should be approximately 0.53. So let's go ahead and grab that, and we'll look that up on table A. So we're looking up a z of 0.53 on table A. So 0.53, there's 0.5 and 0.3, which means that our table A value is going to be 0.7019. So 0.7019 is what we got there. 0.7019. We can put that onto our diagram. The table A always tells us the stuff to the left, so that is 0.7019. This time, what table A shows us is this stuff, which does not match up exactly with what we wanted. How do we find the shaded area? Well, remember that the area under the entire curve has to be equal to 1 to represent 100% of the data. So to find this remaining stuff, we simply do 1 minus this. So our shaded area here should be equal to 1 minus 0.7019, which looks like it should be 0.2981. So that tells us that the probability that a group of 40 flights have an average above 170 passengers is going to be 0.2981. So there we go. So this question here, very similar to part B. The only difference was that, well, it was a different group, so we used a different standard deviation, same formula, standard deviation divided by square root of n, but since the n was different, we got a different value overall. And we had to remember to be a little bit careful when doing the shaded area because we actually wanted the shaded area to the right, so we had to make sure to do 1 minus what we found on table A. All right, well, let's wrap up question 1 by looking at part D here. So for part D, we want to find the probability that on 50 randomly selected flights, the total number of passengers is less than 8,250. So let's see how to do that, because language-wise, that does sound a bit different than the other ones we've done so far. So for part D, we want the probability 50 flights have a total less than 8,250. So the key word in this one is total. Now, whenever you see total, the first thing that should jump into your mind is that totals of groups, remember this is a group of 50 flights, totals can be converted into averages. And if you can convert that total into an average, well, then you can use the sampling distribution. So let's go ahead and convert this total into an average. How do we do that? Well, we know that this is the total that applies to 50 flights. So since this total is supposed to be distributed over those 50 flights, we just need to do division. So a total of 8,250 over 50 flights is equal to an average of 8,250 divided by 50. Well, we can do that. 8,250 divided by 50 looks like that would be an average of 165 over 50 flights. Okay, so this conversion is saying that if you have a total of 8,250 over 50 flights, that's the same as having an average of 165 over 50 flights. It might be actually easier to think about it this way. If you have an average of 165 people over 50 flights, well, 165 times 50 gives us that total of 8,250. So we're going to solve a slightly different question than was originally asked. We're going to try to solve the probability that 50 flights have an average less than 165. So notice we keep the same group size, still 50 flights, but instead of working on something that is about the total, we're going to work on something that's about the average, because that allows us to use our sampling distribution. So now we know how to approach this. This is going to be the sampling distribution. It's not going to be the same sampling distribution as parts B and C, because now the group size is size 50. So this is going to be the sampling distribution with n equals 50. We know the mean doesn't change, so it's going to remain 168. The standard deviation will change. It's the original standard deviation, or the population standard deviation, 24, divided by the square root of the sample size, which in this case is 50. So 24 divided by square root 50. This should give us a standard deviation that's about 3.39. And of course, the shape is going to be approximately normal, since our n is greater than or equal to 30. So this is the distribution we'll use to actually answer this question. So we can go ahead, draw our bell-shaped curve. Okay, middle still located at 168. Our point of interest is 165, which is a little bit less, so somewhere over here. And we want the probability that the average is less than 165. So we'll be shading in the stuff to the left here. Okay, we can go ahead and find our z-score. So z is going to be 165, point of interest, minus the mean, 168, divided by the standard deviation, which of course in this situation, because we're talking about a group of 50, is going to be that 3.39. If we go ahead and do the numerator, that's minus 3 over 3.39. And then if we go ahead and do that division, looks like we should get a z that is approximately negative 0.88. All right, so let's go ahead and look that up on our chart there. So we'll use this guy. So negative 0.88, so we're looking that up on table A. If we go ahead, there's table A right there. I'll zoom out just a little bit. There's negative 0.8 and 0.8. So it looks like the table A value we should get is 0.1894. So we got 0.1894. We can put that onto our table, and it faces this way because table A is always the stuff to the left, 0.1894. Does that match up with our shaded area? Absolutely, right? We wanted the stuff to the left, and table A gave us that. So we can then conclude, I'll have to draw this a little bit over to there. So just put a little separation. So once we get that, we can say that the probability that 50 flights have an average less than 165 is indeed just 0.1894. Now you might say, okay, is that actually the same as the answer we wanted? Well, yes, right? We wanted to get the chance that 50 flights have a total less than 8,250, but as we saw right here, that is exactly the same as having an average less than 165. So it's totally fine to just conclude with this, because this right here shows that this probability is equivalent to this one. So once we know this, we know that that's the same as the answer we wanted. So this first question was all about working with the sampling distribution. You might say, well, didn't we have some sampling distribution questions in practice 7? You did. Those, though, were applying the sampling distribution to a normally distributed population. There we saw the difference between answering questions about the individual, a group having a particular average, a group having a particular total, and a group all doing things. Whereas here, we weren't asked any questions about the individuals because the population was not normally distributed. So the only thing that our analysis would work on were groups having a particular average or groups having a particular total. All right, let's go ahead and take a look at question 2, which starts into sort of the most sort of new topic and the one that is going to be stretching basically into the rest of our course, which is hypothesis testing and confidence intervals. And our first situation that we're talking about those in are what are called the one sample mean procedures. So let's go ahead and look at question 2. So for question 2, we're interested in studying if, on average, people read less books than they did in the past. So according to a nationwide survey in 2000, the average number of books read per year by an American adult was 9.5. So that's what it was in the year 2000. We want to see if that average has decreased. So we're saying that on average, people would read less books nowadays than they did back in the year 2000. So we take a sample of 41 American adults and we get an average of 8.1 books with a standard deviation of 7.2 books. What we're supposed to do is we're supposed to carry out a hypothesis test at alpha equals 0.05. Remember, this alpha is the level of significance. It's set in any hypothesis test ahead of time so that you know what counts as significant evidence and what does not. And along the way, we're going to make sure to confirm all our necessary conditions and state our conclusion in the context of the situation. So let's go ahead and start part A here. We'll actually try to fit in part A just below so that we can reference the information. So right now in our class, we only have introduced one type of hypothesis test, but as we go on, we'll see more and more. So the first thing you should always do is once you see that you need to carry out a hypothesis test, you need to decide what type of hypothesis test it is. Well, the first thing we should keep in mind is that the word average is strewn throughout this, and we see mentions of average and standard deviation. Those are terms that apply to quantitative data. So what we have here is we have something where we're analyzing quantitative data or we're analyzing means. Also, notice that we only have a single sample. Right? We have a single sample of 41 American adults. So we're doing a single sample against a known or assumed average. And of course, that known or assumed average is the average that's coming from the year 2000. So we have one sample quantitative data versus a known average. That makes this what we call a one sample mean hypothesis test. Of course, that's what it had to be because at this point in our course, that's the only one we've talked about. But as we go further, it'll become more and more important that you can identify the type of test. So here we have one sample, 41 American adults. We're talking about a quantitative variable. How many books did you read? And it's going against a known average, this average from 2000. All right, remember hypothesis tests are 5-step processes. So let's go ahead and do that. Let's start with the hypotheses here. So that means we need to write down the HO and the HA, with the HO being the the null hypothesis, and the HA, of course, being the alternate. So in this case, because we're talking about a one sample mean, the form of this should be mu equals something, and mu with some inequality and the same value. So in other words, to fill in these hypotheses, we have two things. We have to decide what value should be there, and then we have to decide what inequality should be there. So let's think about this null hypothesis. Remember, the null hypothesis is your known or assumed average. It's what you would sort of start with if you didn't have any additional information. So in this case, that would come from the year 2000, where we know that the average number of books read per year was 9.5. So that's our null hypothesis. Is if it was 9.5 in the year 2000, without any extra evidence or information, we would think the average is still 9.5. All right. What about the inequality? Well, what is our claim? Remember, the alternate hypothesis is always about the claim. So notice that we're saying here, you want to see if that average has decreased. So our alternate should be less than. So we're saying that if nothing has changed, the average should still be 9.5, but we're claiming the average has decreased below 9.5. We had some language. Whenever you choose a less than or a greater than, we would call this a one-sided test because we have a particular direction that we think the average has changed. We're not just saying it has changed in general. We have a particular direction, one side, we think it's gone down. This, of course, will be important that we make a note that it's one-sided, because when we get down to the p-value step in step 4 and we look on table C, we need to know if it's one-sided or two-sided. All right, so we have our hypotheses set here. Now we need to go to our conditions. So remember, these conditions are things that we need to confirm before we can even use or carry out the test. They're basically saying it's appropriate to run this test based on the data we have. So the first one is that the sample needs to be random and representative. So if we look back up here, we see that we take a random sample of 41 American adults. So this is stated in the question, so we're all good there. Then the second thing we need to do is we need to confirm that the sample size is less than 5% of the population size. Now again, sometimes we don't have information about the population size. If we look here, what is the population that we're studying here? Well, we're studying American adults. There's no mention in here of how many American adults there are. Right? Remember that 41 is our sample size, but that's not the population size. Is there any concern, though, that 41 is a lot of the population? Absolutely not, right? The population of American adults is absolutely massive. So all we would need to say to confirm this is that there are lots of U.S. adults, and that's sufficient. There's no way that 41 represents more than 5% of all the American adults out there. All right, and condition 3. Remember, condition 3, you have two different ways of verifying it. If you have the raw data, you have to check that that raw data looks approximately normal. Or you have to hope that you have enough data. And in this case, we do. We need to confirm that we have more than or equal to 30 data points. Our sample size in this case, if we look back up here, is 41 American adults. So our n would be equal to 41, which is greater than or equal to 30. So we're all good. So all three conditions are satisfied. Remember, I also mentioned in the sort of lecture videos about this stuff that for your class, the conditions are going to be met. You're not going to run into sort of trick questions where the conditions are not satisfied. What's important, though, is that you can explain in these just brief statements here, here, and here why they're confirmed. Well, it was random because that was told to us. Then we're not worried about the sample size because there's tons of U.S. adults out there. And, of course, we do have more than or equal to 30 data points. So it's not a question of whether or not they're going to be true. It's just about making sure you explain why each of them are satisfied. All right, let's go ahead and move to step 3, which is the test statistic. This is the calculation portion. So what is the formula for the test statistic? Well, it depends on what type of test you're running. We're running a one sample mean hypothesis test. So the test statistic is going to be a t-test statistic. Remember, that's because it's not z, because we're having to estimate the population standard deviation with the sample standard deviation. So we have to use a t-test statistic. And the formula is going to be x bar minus mu over s over root n. So that means that to fill in this test statistic, we need to know 4 things: the sample average, the mu, or the null hypothesis, the s, and the n, the sample standard deviation, and the sample size. Now, some of these are very easy, right? We've already mentioned the n. We just used it right here. N is 41. That's our sample size. And we also, this mu, that is our null hypothesis. It says mu equals 9.5. So the only things that are missing are the sample average and the sample standard deviation. And of course, that comes from the data that we collected. So if we look back up here, we see that the random sample of 41 American adults, the average was 8.1, the standard deviation was 7.2. So our average is going to be 8.1, standard deviation 7.2. So there we go. We have all the things we need to plug into this formula. So let's go ahead, put this over here. T equals, we've got 8.1 minus 9.5 divided by 7.2 over the square root of 41. I always recommend doing the numerator and the denominator separately. So in the numerator, we're doing 8.1 minus 9.5. That should give us t equals negative 1.4. And in the denominator, we have 7.2 divided by the square root of 41. That looks like it should give us 1.12. Then let's go ahead and do the division, and we get that t is approximately negative 1.4 divided by 1.12. Looks like we should get t is negative 1.25. So there we go. We have our test statistic. All right, let's go ahead then and convert this into our p-value. So to do the p-value, we have to take the test statistic and look it up on table C. So we're going to be using table C. Remember that for table C, you need to have your degrees of freedom. The degrees of freedom here is going to be n minus 1. Our n was 41, so 41 minus 1 gives us 40 degrees of freedom. Also keep in mind, while the test statistic is negative, when we look up test statistics on table C, we always use their absolute value. So just as a little note here, put this off to the side. We're going to remember use absolute value of t, which is 1.25 when we're looking this up. So our test statistic is 1.25 that we're going to be using to look up, and we have 40 degrees of freedom. So let's go to table C and look that up. So on table C, we have our 40 degrees of freedom. So it looks like we should be right there in this row. So 40 degrees of freedom. We're looking for where 1.25 is located. Notice 1.25 is bigger than this, bigger than this, bigger than this, but smaller than this. So it would put us right there in between. Then we go down to the appropriate p-value. Remember, we have to know if it's one-sided or two-sided. If we go back, what was our claim or our alternate? Well, our alternate was less than 9.5, so it was a one-sided test. So we want to use the one-sided p-value. So let's go back over there. So now that we know where this is located, we're going to follow this down to the one-sided p-value, and this is where we should be between that 0.15 and the 0.10. Remember, we always write this value over here on the right first because it's going to be the smaller one because the p-values get smaller as the t-value gets larger. So we'll write 0.10 and then 0.15. So that tells us that our p-value in this case, this tells us that we have our 0.10 is less than our p-value is less than 0.15. So again, when we're doing these one sample mean hypothesis tests, we don't get an exact value for the p-value, we get a range. So this is telling us that the p-value is somewhere between 10% and 15%. So it might be like 11%, it might be 12.7%, but we know it's not something like 4%, we know it's not something like 29%. It has to be stuck in this range. Even though this is just a range, we can still use it to finish this up and draw our conclusion. How do we actually make our conclusion? How do we decide if we're going to reject the null or fail to reject the null? Well, we take this p-value and we compare it against that alpha that was stated in the question. So we compare our p-value against our alpha, that is 0.05. Again, we don't know exactly what the p-value is, but since it's trapped between 10 and 15%, it is certainly larger than 5%. So our p-value is larger than alpha. Remember, whenever the p-value is larger than alpha, this immediately means that we fail to reject HO. So this is sometimes referenced as the statistical conclusion. We also want to write like the contextual conclusion. What does it actually mean? Well, this means whenever we fail to reject, that means we fail to find evidence. So we would say there's no significant evidence that the average number of books read by U.S. adults has decreased since the year 2000. So in other words, we're saying that yes, our group, the 41 of adults that we investigated, their average was lower than the average for people back in 2000. It was 8.1 versus 9.5. But given the amount of deviation and given the relatively small sample size, we're not convinced that this is far enough away from 9.5 to believe that there has been an overall change in the population. There's no denying that the group of people we looked at had a lower average, but it's not low enough to say that something has fundamentally changed. In other words, they were close enough to 9.5 to believe that them as a group of 41 people was well within normal variation. So we failed to reject HO, and anytime you fail to reject HO, you always begin by saying no significant evidence, and then you just state whatever your claim was. Do keep in mind that it is super important to have that word average in there. So I'm just going to make sure we underline that. Because again, what were we testing in this? Well, we're testing the average. So it's very important to have that statistical measure in your actual conclusion there. All right, so after all that, we've gone ahead and completed part A, which was carrying out this hypothesis test. Now we're going to do a couple quick follow-up things. So let's go ahead. I think we already actually have a blank page, yep. And let's go ahead and talk about part B. So for part B, we're supposed to discuss what it would mean to make a type 2 error in this situation. So a type 2 error. First, let's remember what a type 2 error is. Well, remember, an error means that you make a particular conclusion and it is wrong. So whenever we're talking about interpreting a type 2 error, you have to say what the decision would be and why it would be incorrect. So type 2 is when we fail to reject HO, but HO is false. I recommend writing out each of these pieces sort of separately so that you understand what you need to sort of say to write out this error. So to start off with, let's go ahead and talk about what it would mean to fail to reject HO. We actually just did that, right? We said that was the conclusion we came to. So, I mean, it's nice and easy to write that. It means that we think that there's no evidence that the average has decreased. So we would say type 2 error is we believe there is no significant evidence that the average number of books read has decreased. And then we'll put our little sort of conjunction, our glue word, but in reality, okay, HO is false. So this is what's really true. So HO is false. If we go back, HO being false means that this is incorrect, and the average really is less than 9.5. So we would say, but in reality, the average is less than 9.5. Okay, so what does this type 2 error really mean, or what would be the sort of real life consequences here? Well, this is where you say, oh, doesn't look like anything has changed in terms of the average number of books read, but in reality, the average has decreased, and you missed it, right? Remember when we were first introducing type 1 and type 2 errors, we often described type 1 errors as false positives. You think something has happened, but it really hasn't. And oftentimes we reference type 2 errors as missed effects. And that's exactly what we're describing here. It's where we say, oh, we don't see any evidence for a decrease in the average, but we missed it. There really has been a decrease in the average. Whenever you're interpreting type 1 or type 2 errors, remember, I would always do it in these two pieces. You have to first say what your decision would be, and then you have to say what makes that incorrect. So the failing to reject HO is all here in blue, and the HO being false is actually there in red. All right, let's go ahead and look at part C then. So in part A, we carried out a hypothesis test. The other side of sort of inferential statistics is not about trying to find evidence for things. That's what a hypothesis test does. But in part C, we want to look at the other side of inferential statistics, which is building estimates. So we want to build a 95% confidence interval for the average number of books read by American adults per year. So let's go ahead and do that. We want to do 95% confidence interval for average number of books read per year. Okay, notice that we're doing a confidence interval for the average number of books. So this is going to be a one sample mean confidence interval. Why is it a one sample mean confidence interval? Because we're building a confidence interval for the average of a single group. So it's one sample because it's a single group. And since we're trying to estimate the average, it's a one sample mean confidence interval. Hypothesis tests are always 5-step procedures. Confidence intervals are always 2-step procedures. So the first thing we need to do is think about the conditions. Luckily, we don't need to do any additional work because the conditions for a one sample mean confidence interval are the same as the conditions for the corresponding hypothesis test. Since we've already done the hypothesis test, all we need to say here is that these have already been checked. So we're all good. Then we can move on to step 2, which is the construction. So the construction comes in the form of the sort of formula for this. The construction consists of the point estimate, which is going to be the sample average. That's our base for our guess. And then the margin of error, which we saw was t star s over root n. So to fill in this formula, there are sort of four things that we need. We need to know the x bar, the s, the n, and the t star. So some of these, x bar, s, and n, we've already used, so let's go back and just find them. Remember, our x bar was 8.1, our s was our 7.2, and our n was 41. So this was 8.2, right? That's what we just said, I think. Let's go back and check. Yeah, 8.1, sorry. 8.1. 7.2, and 41. You'll notice that the null hypothesis, that 9.5 value, doesn't show up anywhere here, which should make sense because this is a confidence interval. It doesn't have hypotheses because it's not a hypothesis test. So only the sample information is being used here, the sample average, the sample standard deviation, and sample size. For t star, remember this is based on your confidence level. So to find this t star, we're going to use table C. We still need our degrees of freedom, which remember is 40 here, n minus 1. And we need our confidence level, which we were told is supposed to be 95%. We're going to intersect those two together, and that gives us our t star. So let's go ahead and do that. So if we go here, we're looking for 95%, which is right there, and 40 degrees of freedom. There. Oh, we need to zoom out just a little bit. Okay, so 95%, 40 degrees of freedom, intersect those two together. Looks like we should end up right there at 2.021. So our t star, 2.021. So let's go ahead and grab that. So 2.021. So our t star, 2.021. Keep in mind, this is also why we use the notation of t star as opposed to t. These are very different things. The t is the test statistic that comes from comparing the average from our sample to the hypotheses. The t star is, while it is still based on the t distribution in table C, it's a totally different value. So notice it's a completely different value there. It's based on the confidence level and your degrees of freedom. So let's go ahead and plug all this stuff in. So we have 8.1. plus or minus 2.021, 7.2 over the square root of 41. We can go ahead and get this margin of error first, so you can type that all in together. So 2.021 times 7.2 divided by the square root of 41. Once we have that, we should have 8.1 plus or minus the margin of error, which we should get as 2.27. Then go ahead and build your interval. Remember, always go ahead and do the subtraction first. So 8.1 minus 2.27. The low end of our interval should be 5.83. And then 8.1 plus 2.27. The high end of our interval should be 2.37. We want to make sure we write an interpretation for this. So our interpretation starts with 95% confident that the average, because that's what we're estimating here, number of books read by American adults is between 5.83 and 10.37 per year. So this is how we write interpretations of confidence intervals. We always lead with the level of confidence. Then we say what we're estimating. In this case, it's the average number of books, right? It's not the number of books for all adults, right? It's the average number for this population. And then we say the two values that it's between, the low end 5.83 and the high end 10.37. Notice also, as we talked a little bit about in the lecture videos, there is a deep connection between confidence intervals and hypothesis tests. Hypothesis tests, again, are doing something different. They're looking for evidence, while confidence intervals are trying to build estimates, but they are related procedures. And you'll notice that in this range, 5.83 to 10.37, is the value 9.5 from our null hypothesis, which is why we were unable to throw that value out. Because we're saying, based on our information here, that this range, averages from 5.83 up to 10.37, are all believable. So that average back from 2000, 9.5, is a believable value. So there was no reason to throw it out, which is why in part A, we failed to reject HO. All right, last little quick part here. In part D, we just want to do a quick thing about the interpretation of this. Exactly what does this mean? So part D asks us, could we conclude that 95% of American adults read a number of books between the two values you found in part C? Why or why not? So in other words, we're asking, does this interval mean that 95% of Americans read somewhere between 5.83 and 10.37 books? Well, common sense should tell you that that just doesn't seem to make sense. This is an incredibly narrow range for like almost all of the population to fall between. And the reason that this interpretation is incorrect is that, remember, and this is why we are so careful about including this word average in here, is that this confidence interval is about the average. It doesn't apply to individuals. So what we'd say for D is that this is not correct, or this is not a correct interpretation. Maybe that's a better way of phrasing. This is not a correct interpretation. Confidence intervals for means do not apply to individuals. So it is a misunderstanding to say that this is a range that tells us about where 95% of individuals should land. Instead, we're saying that we're 95% confident that if you took every American adult out there, put them all together, and found their average, that average would land in this interval. So just always be very careful. Confidence intervals do not apply to individuals. All right, that wraps up practice 8.